Okay, so one of the things, in addition to the composition that we can get is the mass. So, for example, we could get the mass of a molecule here, and that would be called the molecular mass. Now, the molecular mass, there's two types of molecular mass that we look at. The standard molecular mass. It depends on the type of chemistry you do. Now, the people who do macroscopic work are interested one, it could be the mass of an average molecule. Because we have isotopes. So we have to worry about the difference in the weight of the atoms. Or two would be the mass of an individual. And so, for example, here we might be interested in just how much does an average water molecule weigh, versus here, if we're interested in the mass of an individual molecule, we might want specifically how much does an H2O17H1 weigh. So we could determine these masses. In fact, let's go ahead and figure out the masses here based on what we talked about earlier about atomic masses. The atomic masses are the same thing. Atomic masses, we have the what we call the average mass of an atom, and then we have the mass of the individual isotopes. Typically, when we talk about atomic mass, we're talking about the average. Go back to chapter 3. Let's see if bring that up. I was going to just show the figure from chapter, actually not chapter 3, chapter 5. Maybe I have it. All right, so these are the individual masses for the isotopes here from chapter 5. So we see the hydrogen atom. There's 2 here. There's actually 3. But what we can do is we can get the individual masses for that. So here, deuterium, how much does a deuterium weigh? Deuterium weighs 2.014101770 U. An oxygen 17 weighs 16.999131150. Hydrogen 1 weighs 1.00 782 50321. And so when I look at the number, I'm going to just sum these up. When I look at the number of decimal places, that's going to tell me how many sig figs I'm allowed. And so looking at this, I see I'm going to have 3, 6, 7, 8 decimal places. 3, 6, 7. We're allowed 8 decimal places in our final answer. This is the rules for sig figs for addition and subtraction. And so the sum of these, will give me the mass of the molecule. So I just add them up. I should say here that to determine the mass, we just sum it up. But I could mention something here. The mass of the individual atoms. That's what we do for figuring out molecular masses. Just simply add up the masses, right? Individual atoms. But no, this does not work for atoms. So, for example, if I wanted to figure out the mass of the, say, oxygen 17, atom, or nuclide, or isotope, I can't do it because Oxygen 17 has 8 protons. And I can figure out the proton mass. Actually, I can look it up in your book. Just get it here. We can get the mass, the subatomic mass of subatomic particles, like the proton, the neutron, and the electron, are known to quite a few sig figs. So, oops, this is answers.com. I don't like that. Shoot. So here we can get it. So for example, the mass of a proton, and we can get this in more sig figs too, is 1.07828 U. And we'll just use this. Here. And so we have 8 protons. That would be 8 times 1.00728 U. And then we have, how many neutrons do we have? We have 9 neutrons. So that would be 9 times the mass of the neutron, which is 1.00867 U. And then we have 8 electrons. 8 electrons will be 8 times 0.00055 U. And we sum it up. What we'll see is that the actual mass of the atom is always less than the sum of its parts. Sum of the masses of the protons, neutrons, and so, in other words, when we add up the masses and we weigh the atom, we get different masses always. And they're off. They aren't off by the same amount each time. They're off by different amounts each time. This is called the mass defect. That's the situation. We have the mass defect. The mass defect arises because of this. Delta M is the loss of mass. Some matter was converted into energy. And delta E, mass converted to energy. Delta E is what we call the nuclear binding energy. The nuclear binding energy is the energy that's required to hold the protons together. All the protons are crammed into a tiny nucleus in the center of the atom. And if we think about it, what does Coulomb's law say? Yeah. Like charges are going to repel, so there's going to be huge repulsion. The protons should scatter from each other. And so what's forcing the protons into a small volume Well, actually, what's holding the protons together in this small bond is what we call the nuclear binding energy. This holds the protons together. If it holds the protons together, then the nuclear binding energy must be much stronger than the electrical forces. Chemists are dealing with this. Electrical forces is what chemists deal with. The nuclear binding energy, this is what the nuclear physicists deal with, or nuclear chemists deal with. This is what we're interested in if you're doing nuclear reactions, like a nuclear power plant or a nuclear bomb or something like that. It's a different type of reaction than what we deal with. What holds atoms together are not nuclear forces. What holds atoms together are electrical forces. For electrical forces, these are insignificant. These mass changes are insignificant, even though they were talked about in chapter 1. And so the easiest way to figure out what the mass of an oxygen-17 is just to sum up the masses of the individual parts, but it doesn't work. You can't do it that way. And since we can't just add up the parts and then figure out what the mass is, how do we figure out what the mass of an oxygen-17 is? How do we figure out the mass of oxygen-17? Well, you weigh it. How do you weigh it? How do you weigh it? Oxygen-17 atom. Where did this chart come from? Well, it came from chapter 5, but where did it come from, this chart? Well, one thing it came from is somebody came up with a definition here. First, you have to define the scale. The scale is U, atomic mass units. And then where did all the numbers come from? Nobody remembers or recalls? The scale came from a spectrum like this. Where did this spectrum come from? Yeah, mass spectrometry. Right, so where did these numbers come from? Well, you have to weigh the individual atoms. How do you weigh the individual atoms? You weigh it using a mass spectrometer. So all these numbers came out of the mass spectrometer, which is experimental. These masses are experimentally determined. These are not determined by calculation. And then you think you might. Isn't the mass defect, isn't that a certain percentage? So, for example, if it costs like this many U's to hold 2 protons together, then 3 protons should be a certain fraction above that. 4 protons, another fraction above it. No, it doesn't. That's because some nuclei are very strongly bonded. Some nuclei are weakly bonded. The nuclei that are very weakly bonded are called radioactive because they don't have very stable nucleus. The ones that are very strongly bonded have very stable nuclei. Those are non-radioactive. But we really aren't going to be dealing with radioactive atoms in this class. So we're just focusing on this. And so it turns out that the percentage of mass that's converted varies depending on the nucleus. The most strongly bonded nuclei, oddly enough, around iron. But anyway, we'll continue with this. So we don't run into this issue with this. When we want to figure out the mass of H2O, we just add up the parts. We don't have to worry about mass defect here at all. There's no problem with mass defect. And so likewise, you'd like to add up the parts of an atom, but you can't add up the parts of an atom because of the mass defect. So we don't figure out the mass. So this is the take-home point. Where do these numbers come from? These numbers come from experimental measurements, once you define this. Where does the mass of the atom? Well, the mass of the atom can be, mass of the molecule can be determined in two ways. One, we can just sum up the parts. And two, we can, just like we can weigh atoms, we can weigh molecules using a mass spectrometer as well. In fact, mass spectrometers are commonly used to weigh individual molecules. Do you know if you ran water through a mass spectrometer, how many peaks you'd get? It depends on the type of mass spectrometer. Some mass spectrometers, because they have to create a charge, on. Some mass spectrometers are very gentle in how they create the charge. Other mass spectrometers aren't so gentle, and they end up fragmenting the molecule into a whole bunch of pieces. But if we had a very gentle mass spectrometer, then what happens is, the molecules can stay intact. They don't get broken apart. And so if we ran just water through a mass spectrometer, how many peaks would we get? If we ran water, although this has other stuff in it, but if we ran water through a mass spectrometer, how many different peaks would we get? Not 5. We did it in class. I'm just saying if anybody remembers the number. I'm sorry? We did it when we did this. We didn't determine the exact mass, we just said the approximate. We figured out how many different combinations there were. How many different combinations were there? It was more than 5. 9. 9, right. Good. That's the number. We get 9 peaks in the mass spectrometer, each corresponding to an individual one. And so if we weighed this one, and we sum up the mass here, and then we measure it in the mass spectrometer, the masses match. The sum of the atoms here is the same as the mass of the molecule itself, determined experimentally. And so no mass defect is the point. But the thing is, though, there are 9 different water molecules that you drink. Do you worry about that? Do you even care about that when you drink a cup of water? You don't even care about that, right? And so for most of us, we don't care about the individual molecules. We just care about the average water molecule. Now, how much does the average water molecule weigh? Well, the average water molecule, we need the average mass of a hydrogen. How do we get the average mass of the hydrogen? We figure out the percents and this, and then we get the number, the black number on the periodic table. And so the average mass of a hydrogen is not on this chart here. It's not 1.078. It's not 2.014. It's 1.00794. And so the average mass, and the average mass we don't call it the average atomic mass. We just call it the atomic mass. The atomic mass is just taken to usually be the average. Whereas, these we would call isotopic masses. This is just review from earlier. And so if we look at the atomic mass of hydrogen is 1.0079 U. We have 2 of those, times 2. And then oxygen, the average mass of oxygen. Now, the average masses are kind of handy to have memorized because they come up quite a lot. And so for some average masses that we use quite a lot, you might find that memorizing some of these will save you a lot of time in the long run. And some of these are pretty easy to memorize. So for example, carbon, I memorize it to 2 decimal places, 12.01 U. These are the average. Now, are you ever going to find a carbon atom in nature that weighs 12.01 U? Does a carbon atom exist that weighs 12.01 U? No. There's no carbon atom that exists that weighs 12.01 U. There are carbon atoms that weigh exactly 12, and there are carbon atoms that weigh 13.00, but there's no such thing as a carbon atom that weighs 12.01 U. Why? Because we're just using the average. We just want, we consume a bunch of carbon atoms, like millions or billions and billions of carbon atoms, then we just want the average, right? If we consume a water molecule, then I don't want to know what each individual water molecule weighs unless I'm dealing with individual. See, if you're dealing with individual atoms, then you need to know what the individual atoms weigh or the individual molecules weigh. Otherwise, you're never going to find one. And so if I'm looking for a carbon atom that weighs 12.01 U, I'll never find it. But if I'm consuming billions upon billions of carbon atoms, it doesn't matter. I'll just take the average. It's like what would be a good analogy? It's like something that's fluctuating, like temperature. Yeah, what was the temperature in July? Do you want to say, okay, the temperature at 9:01 a.m. was this, at 9:02 a.m. was this, 9:03 a.m. was that, right? If you're dealing with so many temperatures, you just want the average. What was the temperature, the average temperature, that day? I don't want to know the individual temperatures because it's too much, right? But if you just happen to be in that space at 9:01 a.m., then you'd like to know the temperature at 9:01 a.m., right? Rather than that. And so it depends on what you're doing. This is the same thing here. Depends on what type of chemist you are. Many chemists that are very concerned about individuals. Right now, we're just interested in the average. And so, anyway, getting back to this, what does prove useful is to have some of these memorized. So the average carbon is 1201, nitrogen is easy because nitrogen is 1401, oxygen 1600. Obviously these can go farther, and so to 2 decimal places, that's all we're going to do. 2 decimal places is enough. If you look at the periodic table, it depends on what periodic table you have. If you get a really fancy periodic table, they might go to 5, 6, 7 decimal places. It'll depend on it. So we got carbon, nitrogen, oxygen. These are probably the most common. And there's one more that's super common. Which one is it? Hydrogen. Now hydrogen, we do 1.01 or 1.008. Okay, because what we want is we want to get 4 sig figs. And so we want 4 sig figs in a molecular mass. And so if I'm dealing with something like H2, do I use 101 or 1008? For H2, I better use 1008 because if I use 101, it's only going to give me 3 sig figs. And so for H2, I can use 2.016. That's how much H2 weighs on average. Although I won't find an individual hydrogen molecule that weighs this, but the average weighs that. Now, If I'm interested in H2O, then I'm not going to use 108, because if I'm interested in H2O, I'm just going to use 202. 202 is going to be easier. And so, I'm not going to get that. I just want 4 sig figs. And so usually I don't carry it out this far. Usually, when we're doing molecular masses and I want 2 sig figs, I'm going to go 2 hydrogens. 2 hydrogens is 202. 1 oxygen is 1600. That gives me 1802. And so the average water molecule was 18.02 U. Now, did you drink a water molecule today that weighed 1802 U? No, you didn't. You drank a whole bunch of other ones that weighed their individual amounts, but on the average, that was it. So that's like the average temperature yesterday or something like that, or the high or the low. And so, so molecular masses, they could refer to this or this. In this class, it's going to refer to number 1, basically, the average. Now, some things don't form molecules. If something doesn't form molecules, then we call it the empirical mass or the formula mass. Empirical mass and formula mass are the same thing. Molecular mass and formula mass are the same thing. Molecular mass and formula mass. All formula mass is the mass of the formula, the average mass formula. So if the formula is H2O2, then what's the mass of H2O? If the formula is NaCl, what's the mass of NaCl? And so formula mass is a little less descriptive. And so we can use formula mass for everything, but we have to use it for empirical formulas. So 1 formula unit is whatever it is. It can be a molecular unit or it could be an empirical unit. And it's just equal to the sum of all atomic masses. So we can just sum up. So for example, the mass of an atom is not equal to the sum of all the masses of the subatomic particles, but the mass of a molecule or the mass of an empirical unit is equal to the sum of the masses of all the particles. Okay, let's go next. So this is carbon dioxide here. Oxygen 1600, carbon is 1201, oxygen 1600. So the average carbon dioxide molecule weighs 4401 U. Okay, calculate the formula mass of ammonium nitrate. So why don't you go give that a try here. Ammonium nitrate is an unusual compound because ammonium nitrate consists of all nonmetals, but it's ionic. And so I told you most ionic compounds are metals and nonmetals. Well, this is an ionic compound that consists of all nonmetals.
I gotta go back to
Did you have some time to figure it out? 80.06. What you guys got? Two decimal places. 80.03. All right. Well, first we got to get the formula. We get the formula here. Ammonium's the NH4 plus, nitrate's NO3 minus. So it's just 1-to-1, ammonium nitrate. And there's, for nitrogen, there are two nitrogens, one from the ammonium ion, one from nitrate. So two 1401s will give us 2802. And then we go to hydrogen. I don't do it this way here because it's going to be rounded anyway. So what we do is 4 times 101. In this case, if I do 101, we got to lose that digit, correct? And so I would get 404 here. This way I can, you know why I do it this way? The reason I do it this way is because then you can do all the calculations in your head. So water, 202 plus 16 is 1802. Something like that. So it makes it quick. Sometimes speed is very important test. 3 times 16 is 48. So let's see what it comes out to. Okay, now it looks like you get 8006. 8006, I would have gotten 8006 myself. because I would have just did 404 here, and then I would have 806. But it's off a little bit. I mean, of course, mine is subject to round-off error. You know, the more digits you carry, the better, the less round-off error you're going to get. But for us, the type of calculation we're going to do, it's okay.
So why did it, in that calculation of the oxygen, the 16.00, but the appearance it was 15.994? Like, I know it, did they just round it, or?
Yeah, 15.999 or 3 nines, right? 3 nines. And so we drop a 9, round it up. Obviously, if you carried the 9s, if you did 15.999, you're going to have a more accurate answer. The thing is the type of calculation we're doing with these is stoichiometry. It depends on the type of calculation. If you're working with individual molecules, then you're going to have a lot of digits here. You don't want to do a lot of round off here, because we're using very sensitive mass spectrometer that can weigh things very precisely. But the type of calculations that we're going to use these masses for the most part, are going to be limited not by this. They're going to be limited by other stuff. And so as long as we get 4 sig figs, we're okay for most applications. You know, once in a while we'll have something like this where we're going to need more than 4. Otherwise, the round off error is going to be too much. All right, now 80.05U, how many grams is that? 80.05U. Well, 80.05U is, well, we can calculate how many, or 80.06U, or let's just look at a water molecule. The average water molecule is 18.02U. How many grams is that? Because a U is kind of difficult sometimes to conceptualize. So let's go with 18.02U equals how many grams? It's the average water molecule. And so the conversion factor is this, 18.02U, there are 6.022 times 10 to the 23rd. This is to 4 sig figs. This number is not exact. There's a whole bunch of numbers after that. But there's 6.022 times 10 to the 23rd U per gram. So we can convert this to grams here. Let's see what it comes out to. So let's just do 18.02 divided by 6.022 times 10 to the 23rd. 2.993. So usually 4 sig figs is adequate for our calculations, times 10 to the minus 23 grams. You know, and so basically we're going to have 22 zeros after the decimal. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and then 2.992 grams. So that's how much the average water molecule weighs in grams.
Can we use that conversion factor? You
This is a conversion factor for U to grams. Or what a lot of people do is they want to know 1U. You know, and so they'll do 1U is how many grams. And so I like to do it, 1 gram is this many U versus 1U is how many grams. And so most books will have this. You just invert it. most books will have this. And so if you look up in the book, it'll show it as 1U is equal to 1.66 ... It depends on how many gigs they do. But this number for me is harder to remember than this number. This number is a lot easier to remember. So I like this number, I don't like this number, but it's the same thing. So, you know, we deal with so little, but, you know, do you ever drink just one water molecule? No. Never do. You know where this number comes from? That number is a special number. This number is so easy for me to memorize because I had it memorized even before you. This number is called Avogadro's number, and it has a special origin, you know. And the special origin is this. You know, for example, Avogadro's number, you know, if I have 18 milliliters of water, do you know how many water molecules I just drank? I just drank an Avogadro's number's worth of water molecules. You know, if I had 18 milliliters of water, I just drank 6.02 times 10 to the 23rd water molecules. If you have 180 grams of sugar, you know what? You just ate an Avogadro's numbers worth of formula units, or molecules, you know, sugar molecules. 180 grams of sugar. If you have 4 grams of helium, there are an Avogadro's numbers worth of helium atoms in that. If you have 63.5 grams of copper, there are 6.022 times 10 to the 23rd copper atoms in there. And so how do I know all this stuff? I know this stuff because of the mole concept. So let's talk about the mole. The mole is the amount of any substance that contains the same number of units as the number of carbon atoms in 12 grams of carbon-12. 1 mole of any substance equals 6.02 times 10 to the 23rd units of that substance. This number is called Avogadro's number or Avogadro's constant. And so what we say is this. Here's the definition. 1 mole is defined as the number of carbon-12 atoms in exactly 12 grams of carbon-12. It's kind of a strange definition. What's the definition of a dozen? 12 is whatever. And so this is a little bit strange definition. All right, and so what you do is you determine. So how do you know how many atoms there are? And so what you have to do is you have to determine the number of atoms. And that number is equal to 6.022 ... times 10 to the 23rd atoms. So, this is what we have here. The mole was chosen this way so that this relationship is valid, so that this relationship arises. Okay. There are 12 U in one carbon-12 atom. And so if I have a carbon-12 atom, it's 12U. In fact, it's defined as 12U. It's exactly 12U. And then there's going to be exactly 12 grams of carbon-12 atoms in 1 mole of carbon-12 atoms. And then there are going to be 6.022 times 10 to the 23rd carbon-12 atoms in a mole of carbon-12. Okay, so it works like this. I can apply this to other things as well. So, for example, there are 12.01 U in the average carbon atom. And so, if I have 1 atom of carbon, then the average weight is 12.01 U. What if I have a mole of carbon atoms? If I have a mole of carbon atoms, then how much does it weigh? Well, it's going to weigh 12.01 grams. And that mole of carbon atoms will contain 6.022 times 10 to the 23rd atoms. So 12.01 grams will give us 6.022 times 10 to the 23rd carbon atoms. And so a mole, 1 mole of anything, is 6.022 times 10 to the 23rd of that. Now, the reason this is a strange number is to maintain this. You know, they picked exactly 12 grams because they have exactly 12 U. If we have exactly 12 U, that's 1 carbon-12. If they pick exactly 12 grams, then count how many carbon-12 atoms there are. And that's why it comes out this strange number. But if it comes out that strange number, then we have this parallel relationship. We can define things. Now let me do a quick aside about the conversion factor here. Is it time? Okay, so let's just do an aside. If you ever forget that conversion factor, then it's very easy to remember. Because what we do is that we just say, okay, if there are 12 U in a carbon-12 atom or nuclide, then they're going to be 6.022 times 10 to the 23rd carbon-12 atoms in a mole of carbon-12. And 1 mole of carbon-12 atoms weighs exactly 12 grams. And so when we look at it, the carbon-12 atoms cancel here. The moles of carbon-12 atoms cancel. Carbon-12 cancels here. This is 12U, carbon-12. And the 12s cancel. And so what we end up with is this equals 6.022 times 10 to the 23rd U per gram. So this is where the conversion factor comes from. The conversion factor comes from the definition of the U and the definition of the mole. So this is the definition of the U. definition of the mole. I don't know why they call it the mole. M-O-L-E. Maybe I should look that up these days. I've never bothered looking it up. Nobody ever said why it's called the mole. But it's like the same thing, you know, why is it called the dozen? Have you ever bothered looking up? No, most people don't care. I think the same thing happens with the mole. Most people don't really care. And so I know this is how I got it. How I figured it out was this. I'm using this relationship in my head. What does the average water molecule weigh? The average water molecule weighs 18.02 U. If I had a mole of average water molecules, how much would a mole of average water molecules weigh? It would weigh 18.02 grams. And I know the density of water. The density of water is 1 gram per milliliter. So this is why I said if I drink 18 milliliters of water, I just had a mole of water. I had a mole of water that's 6.022 times 10 to the 23rd water molecules. How much does the average copper atom weigh? The average copper atom weighs 63.5 U. That means a mole of copper atoms is going to weigh 63.5 grams. And a mole is 6.022 times 10 to the 23rd. So as I said, if we have 63.5 grams of copper, you have 6.022 times 10 to the 23rd atoms. So we can get little relationships like that. All right, we're going to take a break.